are going to discuss how machine learning can be derived from maximum likelihood estimation, one statistical method. So it's kind of looking at linear regression from a probabilistic point of view.
Maximum likelihood estimation, this is a statistical method used in machine learning. It works by maximizing the likelihood function, which represents the probability of observing the output given specific parameter values. So in our data set, we'll be given the input as well as the labeled output, right? So we'll try to maximize the likelihood of the actual output given the input. So to understand this likelihood estimation, let's check one small example. If you are estimating a coin's bias, so let's say you are flipping the coin 100 times and you get 60 heads. So the MLE or maximum likelihood estimation says the most likely probability of heads is 0.6 because that value best explains your data. So here if the data comes from different distributions, for different distributions we have different formulas for calculating this maximum likelihood estimation. We'll see linear regression from this perspective here. So in our linear regression video, we discussed this problem, calculating the house price based on house area, number of bedrooms, number of toilets, number of balconies. So this data set we had n data samples, x1, y1, x2, y2 till xn, yn. So for all I equals to 1 to n, xi's are d-dimensional because we had multiple parameters in our input. So xi's are d-dimensional, yi's are the house price, this is a real value. Our predicted output was a function of the xi input. Xi was d-dimensional, so our function was a function of d values. So in a d-dimensional space, we found this straight line equation w0 plus w1 xi1, w2 xi2 till wd xid, which we can simplify as w0 plus k equals to 1 to d summation wi xik. This is the basis. So again, if we want to simplify this thing with a vector multiplication, we can get one vector w, which is combination of w0, w1 till wt. So this is a d plus 1 dimensional vector. Xi's we updated because we added 1 here and xi also became a d plus 1 dimensional vector here. So fxi then we can write as a vector multiplication as w transpose xi or xi transpose w. So the model output for ith term xi is fxi, that is a w transpose xi or xi transpose w. The error for each ith term will be ei, that is yi minus fxi, this is the actual output and this is the predicted output. The error for each point is basically the distance from the point to our line. If this is the best fit line and these are the actual data points, so these distances are the errors that we want to minimize. So in our previous linear regression video also we saw our objective function is basically to minimize the sum of the square of the errors. We are taking square because the errors can be positive as well as negative. So this ei basically is yi minus fxy or fxi minus yi. So which is w transpose xi minus yi square. These things we want to minimize. So let's say error for each ith term is ei equals to yi minus w transpose xi, right? So considering n data samples, if we are taking all the errors in one vector from e1 to en, we'll get this e vector. Now we got this best fit line, right? So instead of that we can get this line as well or this line as well, right? But this two lines, this two doesn't match our data. Only if we get a perfect line, then only that is matching with our data set. So if we get a perfect line, then errors will be symmetric around that line and errors are likely to be small than large. So we can assume the errors are distributed from a Gaussian distribution with mean 0 and variance sigma square. So these errors are coming from a Gaussian normal distribution with mean 0 and variance sigma square. Now these errors are coming from this distribution. Let's say for n data samples we get this x vector, that is x1 to xn. This is basically a matrix because each xi is a d-dimensional vector. Y is a vector of all the actual outputs y1 to yn. E is basically a vector of e1 to en, all the errors. So y will be w transpose x plus e. This is the actual output is equals to predicted output plus the error. This e is coming from this normal or Gaussian distribution, right? So this is dependent on e. So the dependent term y is conditionally normal with mean w transpose x and variance sigma square. Variance will remain the same. So this actual output y, this is coming from this Gaussian or normal distribution with mean w transpose x and variance sigma square. So if this actual output is coming from this Gaussian distribution, we can calculate its likelihood using this formula. So this is the formula for likelihood of Gaussian distribution. So we are trying to calculate the likelihood of y or likelihood of the actual output given the input, which is 1 over root of 2 pi sigma square e raised to power minus half this y minus w transpose x divided by sigma's whole square. So this is the likelihood, and we want to maximize the likelihood of the actual output given the input. So if we take the log likelihood for ease of computation, the log of this term will be log of this plus log of this. Log of this is minus half this term. So this is the log likelihood. So we can maximize this as well. So we are maximizing this log likelihood. You see, our variable is w here, and then this part we just have the constant. We can just ignore this part. We can just maximize this minus half this whole term. So we are maximizing this whole term, or we can just minimize half this term, or we are minimizing y minus w transpose x whole square divided by 2 sigma square. This is the thing we are minimizing. But here also this sigma is a constant, right? So we can get rid of that as well. So our objective is remaining minimizing y minus w transpose x whole square. So this is the same as a squared error, right? So that we discussed in our linear regression video. So if you try to view this problem from maximum likelihood perspective, then also we are getting this squared error, and we can minimize this squared error or the mean squared error.